why Microsoft is talking about open source. Well, today, Microsoft is actually in love with open source. And the reason for that is simple. Microsoft is cloud provider. And that means that we win immediately when our customers choose to use Azure Cloud Service. And for that reason, we embrace open source. And actually, the mission of our team and Azure AG Inside Service is to help our customers succeed using open source in the cloud. And that's how we have a chance today to talk about what's possible with the open source components and how we can connect these open source components today to build interactive environment to work with big data. So we'll take a tops-down approach. We'll start with overall architecture of the solutions that we have. And then we'll dive into each individual piece to describe how it works together, how they work together. And finally, in the end, we'll talk about resource management challenges raised by the fact that when multiple concurrent interactive applications run in the same cluster, you need to somehow manage resources between them. So we'll talk about that and about some solutions that we have of resolving that challenge. But before we get started, or to start things off, let me start with asking you a question. What is your top concern for big data projects? Think about it for a minute. At Microsoft, we have a privilege of working with many large enterprise customers of different kinds. And in one of the most structured kind of discussions and studies that we do with customers, we had the opportunity to talk to 3 groups of customers, 20 customers each, and ask them this question. And it was surprising that across this group of customers, there was one single reason, one single top concern that bubbled up that was shared by majority of the customers. Can you guess what it was? If you have a good guess, just shout out, and it might be interesting for us to compare what we got and what you have in mind. I hear scaling. Performance, platform. Security. Well, the set of concerns is broad, and some of them actually have relevance to what we got as a most commonly shared concern. What we got from customers was length of development cycle was a universally shared concern across them. And there are a couple of things that I like about this particular framing or description of this problem. The first is that it's not just a problem statement. It is actually a metric that we can monitor, we can measure, and improve. For example, if you debugging some big data job and need to get access and find some logs, and it takes a long time, we can measure it and fix it. Or if you have machine learning experiment that runs like in 5 hours, then this metric will clearly tell you, will clearly flag this long-running experiment as a potential problem. And in big data reality, we sometimes accept things as kind of laws of nature, like processing big data, especially with complex algorithms, should take a long time. But if this long-running job is part of your continuous or repeating development cycle, it causes a problem. It is a problem. So that metric forces us to look critically at what we are doing and find mitigations for those problems. And in this example that I gave, there is actually good mitigation or good solutions like sampling and scaling out on demand that cloud provides, which we'll talk about in more detail later. And another interesting thing about this metric or problem statement is that it's also a good proxy for 2 important factors that govern success or failure of our big data projects, namely productivity and project risks. There is a clear connection between productivity and length of development cycle. If development cycle goes longer, productivity goes down. But it's not as clear how much productivity goes down. If you have an engineer or developer who needs to do his job and while doing his basic kind of increment of work, he needs to wait for half an hour or for some extended period of time. Then suddenly this engineer kind of lost his ability to think with the speed of his thought. Now, in order to make any next step, or in order to make any next conclusion, he needs to wait for this process to complete. And that drops your productivity into 0. It's not just lowered, it's 0. Another thing about project risk. Projects that depend on long development cycles are vulnerable to unknowns. Imagine a project that you try to run on time or on some fixed budget, and suddenly, as it usually happens, there are a couple of things that were discovered during project development. And these couple of things require you to run 100 more iterations of long things. And that translates into 2 weeks of additional time. Well, at this point, there is no flexibility in the system anymore. You are going to fail your project and not deliver on time or extend your budget, but there is no flexibility in the project that depend on these long development cycles to accommodate for unknown. So those things are important. And if we decide that, hey, this is a project, this is a problem, this is the number one problem that we want to go and solve. So how do we go about it? Well, there are multiple parts of development process. And if you want to solve this development cycle problem, we would go in a holistic way and apply this criteria to each part of the development process. First, during data exploration and experimentation, we would like to have an environment, very iterative environment, where we can play with data and understand the data in a very quick, REPL-like manner. So we need interactive experience for that. Well, once we discovered some understanding, or once we gained some understanding of the data, we would like to have a seamless way to share these data assets and insights with our team and with the organization at large. So we need some effective data sharing tools. And on the next stage, when we are ready to productize this data pipeline and move it into production, we need some reliable source code controlled mechanisms to develop these code artifacts. And finally, once we have everything running in production and something bad happens, we need efficient tools to debug our problems quickly so we don't spend, again, time on debugging of the big data pipelines. So we took these 4 phases of development and put together a combination of open source projects, and we improved some of them. And this is our architecture of what we got as a result. So all of these projects are open source, with the exception of the BI tools. Unfortunately, doesn't seem to be some fully fledged BI tool that is open source. And you can potentially use this architecture and replicate or install it on your own Spark cluster. Or you can use Azure Cloud and just in few clicks deploy Spark clusters that will have all of these components pre-configured for you. On this diagram, you can see Jupyter notebooks are used as to solve the first part of the problem, where we provide the environment for interactive data exploration and experimentation. IntelliJ IDEA is the environment that is used for development of your production code artifacts and for debugging of your big data pipelines. And BI tools are used for data sharing. Libby Server in this picture is used to connect our interactive tools to a Yarn resource manager. So it manages Yarn applications, Spark applications in Yarn. And given that this architecture is designed for the cloud, we also have, in addition to the local HDFS, we also have cloud storage systems, such as Azure Blob Storage and Azure Data Lake Storage. So now we can jump into discussion of all of these particular ingredients in more detail. So let's start with Jupyter notebooks. Actually, no, before we start with the Jupyter notebooks, let's cover the basis, like the Spark itself. So why we need to answer a question, why do we use Spark as our platform for interactive data analysis? Well, the first simple question is, Spark is interactive by default. If you run some trivial task in Spark, it will return to you immediately. So this is unlike Hadoop, where there is huge overhead, or not huge, at least significant overhead of launching the tasks, that the default response time in Hadoop is much higher than in Spark. And if you move towards bigger data sets, there is even a promise from Spark that you can remain interactive as if you use its in-memory technologies. So it allows you to cache data in memory. And if you use that technique and ensure that the size of your cluster is sufficient for the data set that you're handling, you can expect to achieve interactive response time even when you work with large data sets. There is a caveat here is that memory is the most expensive resource in our clusters. So if you make a big bet that, hey, my interactive experience will depend on that technology, you're signing up for significant budget for your clusters. So it may not work all the time. So you need to be mindful about how you kind of plan capacity of your clusters. And finally, small thing, but it is important, as you'll see in the kind of reminder of the session. Spark also has built-in functionality for sampling. And that is important kind of mitigation technique to fight your battle against the big data. And we'll talk about it in more detail later. Another factor in favor of Spark is that the community around Spark is actually serious about efficient data processing at scale. So there is a Tungsten project in Spark that already delivered some speed ups when you're trying to run a really big data job on it. And in Spark 2.0, it will come to fruition and deliver additional speed up on top of that. So it's good to know that we are using the technologies that is kind of a cutting edge in terms of speed of processing of big data. There is also interesting new features that are coming that integrate Spark streaming with interactive SQL. That is very interesting, but streaming portion is out of scope for this talk, so we'll not talk about that. And final point is Spark seems to be a reliable bet today. Like there are many large companies, including Microsoft, that made a bet on Spark and contributing to it actively. There is a great and active community around it. So these days, Spark is becoming ready for enterprises. So Spark is interactive, that's good. But there is another aspect of Spark that is very important for our interactive journey. And that aspect is its platform capabilities. So Spark is not just interactive compute engine. It also gives you a comprehensive platform. So if you're familiar with Hadoop Vault, then you know that if you want to do SQL, you would use Hive. If you want to use state-of-the-art ETL tool, then you would use Pig. And if you need to do machine learning, you would use Mahout. So that's all great, that's great tools, but unfortunately, there is nothing in common between those tools. Every time you use one of those tools, you need to learn your way from bottoms up. Just MapReduce paradigm or MapReduce engine behind Hadoop was just not expressive enough. It was just low enough that people needed to build their own frameworks and their own APIs on top of it. And that's what Spark changes. Spark offers kind of a more generic compute engine that allows workloads that run on top of it to express their computational needs in the form of these computational graphs that Spark provides. And that connects things together. The first thing that it gives us as a developers that we no longer need to learn multiple things. Like if you learn Spark once, we can apply this knowledge across all of the workloads that run on Spark. And second, these workloads can actually be connected together. You can run graph processing and connect it to machine learning and vice versa. So they all use the same kind of platform. So it's important to know that while Spark kind of brings better things into Hadoop Vault, it's not necessarily replacing Hadoop. We are still using Yarn as a resource manager. We are still using HDFS as a file system or just Hadoop file system abstractions. So Spark is not replacing Hadoop, but it's reshaping it and bringing it more structure. And that structure allows us, in the interactive world, allows to build experiences that when they are built once, they can be applied to multiple things. So if we build interactive experience for Spark, we will be able to use the same kind of environment to work in SQL, in machine learning, and in other workloads that Spark provides. That's kind of empowering theme for experiences building. So another component of our solution is the cloud itself, is a cloud platform. So let's talk about it for a moment. So Spark on Azure Cloud is offered as a managed service. And what we imply by this managed service is that there is engineers and processes behind our Spark clusters in Azure Cloud that provide you with notion of SLA, service level agreement. We promise that Spark will work as expected for you once you deploy it in the cloud. There is an on-call team that 24/7 monitors our clusters, and if something goes wrong, this on-call team will go and fix things for you, so you don't need to. In our cloud, we also use, we partner deeply with Hortonworks in these Hadoop things, and in our clusters, we use Hortonworks distribution. And that brings in another angle of our managed Hadoop and Spark offering, where if you have any problem, support question, or just bug fix that you need to fix, Microsoft and Hortonworks engineers will work with you on fixing it and delivering the fix to you and to the community at large as well. So that's basically the most important things about Azure Cloud offering. On top of it, as we discussed in the previous slide, we have a set of tools that provide interactive experiences. And before we go to resource management, let's switch to the demo and talk about Jupyter. And for that, we'll need to switch. Yeah. Thank you. So to give you context, we are in Microsoft Azure portal, so that's Azure Cloud. And the specific service that we'll talk about is HD Insight. So if you click on HD Insight clusters, you'll see the list of clusters that we have. At any moment, you can create a new one just by clicking an Add button, specifying the cluster name. Let's give it a minute. Let's say demo. And in here, you will be able to specify a type of the cluster. We have Hadoop and other types of clusters, including Spark. And for Spark, we also have two variants of Spark, standard and premium. And if you attended Keynote, you saw a little bit of the premium cluster type, which is actually our server running on top of Spark. So at any moment, you can opt in into using Microsoft R server for your machine learning tasks. So another interesting thing to highlight here, let's select standard Spark for now, that you can configure what resources your cluster uses. So by just going to the pricing tab, you can specify the size of the cluster, and later on you can always rescale your cluster on demand and choose what VM node type you want to use. So starting from smaller ones to bigger ones that are more optimized for compute-intensive tasks. So let's switch back to our clusters and take a look at the existing one. So this cluster dashboard gives you basic information about cluster, including the scale tab. And also, within the cluster, we have several management dashboards. Today, we'll talk about the Jupyter notebook, but there is also entry points for the YARN management UI and just overall cluster management as well. So let's open the Jupyter notebook. So the Jupyter notebook is a tool that is very popular in the Python data scientist community. And back in the days when we started working on it, there is another alternative that is also popular with Spark community, which is Zeppelin. So just to give you kind of an overview of all of the potential options that you can have. So you don't have to use Jupyter, you can also use Zeppelin. But back in the days when we started, Zeppelin didn't support kind of a remote job submission to Spark cluster. So we went with Jupyter and customized and optimized it to provide experiences integrated with Spark. So here's a list of notebooks that I have on my cluster in this Jupyter notebook server. And I just opened one of these notebooks, which is a notebook which showcases some of the features of the integrations that we did for Spark and Jupyter. So underlying this integration are two components. The first component is an extension point for Jupyter itself, and in Jupyter world, extensibility is done through the notion of kernels. So we created a kernel that, that connects Jupyter to a Livy server, and Livy server is a Spark job submission service that allows us to create interactive sessions that allow Jupyter to send the commands that we type or create in the cells of the Jupyter to Spark cluster and receive back results. We also optimized or modified Livy to provide some of the high availability features that are important for our enterprise customers. So Livy originally was not able to recover its state after some interruption fork. Like if the reboot happened or Livy server would go down, it would come back up and all of the interactive sessions would be lost. So we did the work to externalize the session state into a Zookeeper, which is also part of our clusters. And now whenever Livy fails or restarts, sessions are not being interrupted and you can continue work in the Jupyter without notice. A couple of interesting features that are available as part of this Spark kernels that we've built is the first is info magic. So these percentage things in Jupyter terms are called magics. So info magic allows you to get access directly to a Spark UI. So if you want to look at, hey, what's going on with my notebook, how jobs are being processed, you can always get this direct link without going through the yarn management and things like that. And if you need to look at the driver logs, which sometimes is a difficult task, there is also a direct link for driver logs as well. So that's one first small feature. Another thing that we integrated is inline support for SQL with automatic visualization support. So if you are to run this SQL query, we'll get the results back in a tabular format, and then we'll have ability to quickly switch from the views to visualize these results. So that helps in our tasks of kind of data discovery and visualization. So now for this sample of some web activity, we can see which states have a most activity in this sample data set. And finally, in order to kind of take advantage of all of the good work that Python community did around Jupyter, we also enabled usage of Python native visualization libraries. So this percentage local magic allows you to run any Python code and use any of the visualization libraries available for Python. That will enable some powerful visualizations that are available in the ecosystem to be used directly in your Spark projects. So this is kind of a map visualization that you can use. So let's move forward. So next notebook that we would like to take a look at illustrates how we can go about this journey of interactive data analysis using notebooks. So in this example notebook, we have a New York taxi data set that captures trips and fares paid in the New York taxi. And we can go through the steps of kind of analyzing it. The first step would be just to load the data. So here I have a JSON data set, kind of original data set of 200 gigabytes in size. And I can quickly load kind of a beginning of this data set and take a look at that. So I can see that, oh, it's JSON. Fortunately, Spark has built-in mechanisms to just infer JSON schema. But sometimes it takes a long time. So we use here a little bit of additional code here to make this data schema discovery fast. And we can keep our experience of analyzing this data set kind of interactive. So now that I have read this data from the JSON file and converted it into a Spark data frame, it is now in tabular format, and we can use embedded SQL cell to start querying this data set. And we can take a look at the columns that are available and start kind of making sense of this data. The next step would be to kind of start shaping and forming this data set. In this example, we are dropping some extra columns and doing things with it. And after we have kind of cleaned up our data set, we are ready to start working with it. And there are two two ways we can approach that. First, if you are going to use BI tools, we would like to keep the full data set, so our answers in the BI dashboards kind of are representative. And for that, Spark has integration with columnar formats, where you can store the full data set in an optimized form and kind of use it in an interactive way in your BI tools. So for that, you can use the save as table statement to save it, and it saves by default as a Parquet format. And second, more optimal from the data exploration point of view is the sampling. So it's frequently kind of a trap of the big data. When you have your script ready and it produces result, but it's not exactly right, you say, hey, I'll just change this little thing, and next time it will be right. And then you wait again for this large job to proceed. So whenever you do this, you should actually stop and cancel your job and go back and actually convert your full data set into a sample data set. Never kind of play with the full data sets. Do your development work on the kind of small sample, get to the final stage, and then, only then, kind of rerun your job on the full data set. So Spark has built-in sampling feature, which is just sample, which makes it extremely easy for you to sample the data. So I pre-run these statements because they take some time to kind of get us to the next stage. So now that we have our samples and full data set in Parquet format, we can proceed with next step to understand the data. So we can run task to again kind of understand something about our data set. In this query, we say, hey, what is the distribution of passenger counts in this data set? And we can see that in the sample data set, so this was a query that ran quickly because it was sample. From the sample, it produced some distribution of passengers. But what if I kind of not sure if this sampled result is correct or not? Well, at any moment in time, I can go back and say, hey, I have cached my full data set, and it's in columnar format, and I can switch back to my cluster dashboard and say, now I want to run this data set on the full data set, so run this query on the full data set. So I need to scale my cluster. So I already scaled it to 20 nodes, so it will work fast. But at any moment, you can say that, hey, I need 200 nodes, and run your query and then scale back. So that gives you a power of kind of scale out on demand and run your queries very quickly when you need to. So let's run this data set. Oh, sorry, query keeps switching to data set word. So it runs against the cached data, and if it's still cached, it should return very quickly in a few seconds. Yes, it did. And now we can plot this data coming from the full data set and compare the distributions. So you can see that the results that I get from the full data set are about 1,000 times greater than the results I get from the sample, but the distribution is exactly the same as the sample. So my query over the sample data set was representative. And what follows is we can continue doing these experiments with data. We can build some histograms about the data set that represent what is the dependency of the tip amount and fare amount and things like that, and proceed even further using our sample data set to build our machine learning model. So we can do feature engineering, and I pre-run these cells so we don't need to. We can extract these features and send them to machine learning job. We can skip over this quickly. And finally, we can build do training of our machine learning and compare the results and arrive at some conclusions. So that's a result of our machine learning model that we trained in this notebook that compares actual tip amounts with predicted tip amounts for this data set. So once we have achieved some of the results in our kind of exploratory notebook, the next step would be to share this data with our team. So fortunately, all of the work that we did with tables here, when we saved the table into a Hive table, all of this is available for BI tools to consume through Power BI or Tableau or Qlik or whatever Power BI tool you use through ODBC connection to the cluster. So we can say, hey, connect to the data select Spark. And by specifying the URI of the cluster here, we can connect to our cluster and then see all of the tables here. I have already pre-created it. So we can go back to my workspace. And here's one of these data sets. So the train data set and taxi train full data set is available for me here. So I can start building some reports. This is a result of the reports. In the interest of time, we won't build one on stage right now. But Power BI, just similar to what Tableau provides, gives you full kind of capabilities of rich visualizations in the web and in the client form factors. So that is the BI tools. And moving forward, once we kind of productized our, once we gained our understanding and shared the data, we want to productize our data artifacts. And for that, we've built, we used IntelliJ IDEA, and we built a plugin for it that connects it directly to clusters in Azure HD Insight. So in here, I have a simple sample that runs some trivial job. And in here, we can just, using our plugin, we can right-click on the project and say, submit this application to HD Insight cluster. And it will prompt me for my credentials. Connects me to Azure subscription. And then, oh, yeah, I should have. Two-factor authentication these days is a norm, so that slows down your demos sometimes. And once I'm authenticated my Azure subscription, I can select cluster to which I want to submit this job, and everything else will be done for me by this plugin. So it streamlines your development job while you're working in this environment. So I'm selecting the cluster, I'm selecting the class that I want to be executed as part of this job submission, and I can click submit. So that's our IntelliJ plugin. In addition to this simple job submission capabilities, it also offers you ability to browse through the content of the storage accounts, and something more interesting, it also supports kind of remote debugging capabilities. So from your local machine, you can connect to your Azure HD Insight cluster using virtual network connection, and then submit your job directly to the cluster. That allows you to run the driver of the Spark job on your local machine and debug what's happening with it. So now that our job submission through the UI succeeded, we can click debug on this remote job submission, and it will kind of establish a communication channel with our cluster, run the Yarn application on the cluster attached to the driver that is running on my local machine, and hopefully it will hit the breakpoint that I set up in the project. Let's see if that part works. So this ability to run your, to debug your jobs that are running on the cluster is really powerful technique. Oh, yeah. So we got our breakpoint, and potentially that allows us to investigate what's happening with my job while it's running on the full data set in production. So for the scenario that we mentioned, where, hey, I have my data pipeline running and everything is great, but suddenly something bad happened. How quickly can I debug what is this that happened? Well, with this remote debugging capability, you can just pause your job in the middle of what it was doing and investigate what variables happen to be on the real data set and understand what's happening in real time. Okay, so now let's switch back to the slide deck. Okay, and we can spend the last minutes of this talk talking about the resource management challenges that we had. So if you go back to the architecture diagrams that we had, you can see that there is multiple Spark applications running in Yarn. And all of those are interactive applications. For example, if you take a notebook application and the Swift server, they both need to run at the same time. Like Swift serves BI tools, kind of serves the SQL queries to them, while I'm working on notebook doing some data exploration. So they need to work at the same time. But if there is no queries that come into the Swift server, I would like it to not consume any resources from my cluster, and vice versa. So how do we accomplish that? Well, if you notice on this diagram, we use different Yarn queues to run these different applications. And that allows us to use a couple of features in Yarn that allows these applications to share resources between each other. The first feature is dynamic resource allocation. So we configured Swift server, which serves ODBC queries, to use this dynamic resource allocation. And that means that by default, if there is no SQL queries coming into the cluster, Swift server will use 0 executors, so it will not use any resources. And when queries come in, it will dynamically request Yarn for new executors, and it will get those resources and will be able to fulfill these SQL queries dynamically. So you might question here, hey, what happens if the notebook that is running on this cluster already uses all of the resources of the cluster? How Swift server can demand more when there is nothing left? Well, the preemption feature, Yarn preemption feature, helps with that. So we configured it in such a way that whenever Swift server asks for more resources and there is not enough, Yarn will take away executors from the notebook applications and give it back to Swift. And eventually, if there is concurrent workload happening in both applications, it will actually use fair resource management policy and give equal share of resources to both of these applications. So that works pretty well, but there are a couple of problems that we discovered. First, there is some bugs in Yarn that prevent us from using full capabilities of it. Like there is a notion of the dominant resource calculator that, opposed to a default resource calculator, allows you to use CPUs to govern how resources get allocated. Well, unfortunately, that one doesn't work. It breaks the preemption logic. So we couldn't use it in the current iteration. We use just default resource calculator for that. And there is also more kind of feature limitations as well. Like there is no notion of preemption between applications. And that means that for our notebooks applications that run in the same Yarn queue, end user needs to kind of manage resources between them manually. So that's suboptimal. And we are working with Hortonworks and with the community on fixing those, or in introducing these fixes. And another limitation is what would be even better if applications were able to share. Actually, it comes from the Livy side. So Livy server that submits these Spark jobs, it would be nice if it was able to share resources between different sessions. And today that capability is absent. So our team is actually working on implementing that capability and bringing it back to community so we can have even better kind of interactive experience. That's our kind of experience with that. In summary, here is a list of all of the components that we discussed with some of the alternatives as well. That's for your reference. And another slide is about resources, where you can learn more about the open source projects that we discussed, as well as learn about Azure AG Insight. So with that, I'm finishing my session. Thank you for attending, and I appreciate your attention.